In this video, we present our work, High-Quality RGB-D Reconstruction via Multi-View on Calibrated Photometric Stereo and Gradient-SDF. This work was done by Lu Sang together with Bjoern Haefner, Xingxing and Daniel Cremers. High-quality 3D reconstruction is in high demand in different fields. To obtain a complete, consistent 3D model, surface representation strategy is crucial. One common surface representation method is to use a sun distance field. Meanwhile, camera pose need to be given or estimated. However, normally, the model needs to be refined to get details on the surface. One of the geometry refining strategies is using photometric stereo technique. Photometric stereo studies the relations between environment lighting, reflectance, and surface normal. Surface quantities can be solved by minimizing the PS energy after building a suitable image formation model to describe the given images. However, if one initializes the geometry using sun distance field, the surface point positions are not stored explicitly before running surface extracting methods on the voxels. Thus, the image formation model cannot be built on the actual surface. There will be a gap if we directly build the image formation model on the voxel center. For the camera pose estimation part, the two problems. First, most methods that estimate camera pose prefer point cloud because they need to project points back to the images. Second, if they minimize the photometric error, it normally assumes that color is consistent across the images. This contradicts the fact that in the image formation model, point color could also depend on the view angle and light condition of the view. To tackle these problems, we adopt Gradient-SDF to represent the surface. The surface point is located by moving along the gradient direction with the length of the distance. It also allows us to project the actual surface point back to the image. In this paper, we propose two image formation models to deal with two different types of scenario, natural light case and point light source case. In each case, the model contains pose variable, lighting variables, and surface quantities, namely distance and albedo. We jointly optimize all the variables in an alternating manner. In the end, the multi-view photometric arrow minimizes the residual together with the Haefner regularizer, which ensures the solution stays as an sun distance field. To summary, the complete pipeline of our work is as following. Given an RGB-D data sequence, we first use only depth images to minimize the geometry error to estimate the camera pose and initialize the Gradient-SDF volume. Second, we use the RGB images to minimize the voxel PS energy to refine the lighting, surface quantities, and camera pose. To verify the camera pose refinement part, we compare with other state-of-the-art tracking methods. It shows that our method achieves better results. Moreover, compared with the initial camera pose, optimizing only on the voxel center, it proves that the proposed method that optimizes on the surface points indeed improves accuracy. The second part, we focus on the geometry improvement of our method. After refinement, the detailed texture are recovered compared to the initial result. We also evaluate our method on the multi-view dataset where the ground truth laser scan of the object is offered. Our reconstructed model obtained better accuracy compared to the previous work. The code is publicly available. Thank you. Hope to see you at our poster.